So in this video I'm going to be going over systems of particles. So imagine that we have a system of particles consisting of point objects. So here's some particles in space. And relative to some coordinate system, I'm going to say that each particle has a mass of mi and a position vector of ri. So for example, this is r1. Let's make it r1, and we can pick another point as r2 and mass m2. So this system of particles is just a collection of particles that I've selected arbitrarily and said that's a system. And we're going to identify common things that we find in a system of particles. Well, one commonality is that once we define the system of particles, we can define something called the mass of the system. So assuming there are n particles, so it'll be the mass, which is the total mass. I'll use a capital M. We can also define something called the center of mass. The center of mass is a weighted average, right, of all the points in the system. So for example, weighted by the mass of the particle. So that is to say that the center of mass is really the weighted average of each particle I. Of course, m is the total mass, and m of the system of particles. We can pull out the m and we get the RCM is equal to 1 over m. Where Ri is the position vector of each of the particles. So let's just make sure we understand what the meaning of the total mass of the RCM is by giving an example, just to make sure we understand it before I start switching over to integrals and continuous distributions. So imagine that we have a mass of M1 is 1 kilogram, and it's located at 2i plus 3j plus 2k. And then we have a second mass located at, and it's 2 kilograms. And we assume all these are standard units. There's going to be kilograms, meters, and second SI. So these are in units of meters. Here is R2 vector, and we'll say this is 1i minus 2j plus 3k. And M3, I guess if you know the standard units, I'm not going to keep writing kilograms and meters, but I'll just assume it's, so let's say it's 3 kilograms. R3, the position of the third mass, is given by 2i minus 4j plus 6k. Okay, great. So we now know the positions and the mass of each of these particles, and we'd like to calculate the total mass. So these are two properties of a system of particles. We can define the mass of the total mass of the system of particles, or the center of mass of the system of particles. And later we'll be talking about the velocity of the center of mass of the system of particles, and then including angular momentum of the system of particles, and the momentum of the system of particles, the velocity of the center of mass, the acceleration of the center of mass, the torques on the center with respect to the center of mass. So these are all ideas, but these are all collective properties of a system of particles. So we have one. So we know the total mass m is just m1 plus m2 plus m3, which is really the sum taken from 1 to 3 of mi, which in this case is 1 plus 2 plus 3, which is equal to 6. The RCM, the center of mass, the position vector of the center of mass. So if I had a system of particles, you're expecting that the weighted average should be somewhere in the middle of these center of particles. So it's somewhere here. So the center of mass position, right, is some point. It might not be pointing to any point, but it's some position in space, right, that's in the interior of the convex hull of the system of particles. So anyway, so this is 1 over m times the sigma of mi r I. So in this case, this would be 1 over 6 times 1 kilogram times 2I plus 3J plus 2K plus 2 kilograms times 1I minus 2J plus 3K. And then I'll put this over here, 3 times 2I minus 4J plus 6K. So I won't evaluate this because it's not worthwhile the attempt to actually work on this. It's just the procedure is what's important. And okay, so once you've understood this, let's now move to continuous systems of distributions. So again, we're going to be looking at, I'm going to principally dominating this idea on the total mass and the center of mass, or CM, the center of mass. So this discussion will be on just center of mass and position. So now let's assume that we have a distribution. So again, we have a system. It consists of a continuous distribution of mass. So here's the distribution. Assume that some mass element. There's a mass element dm, and relative to some coordinate system, we're going to define this little piece of matter, dm, has a position vector of r. And we'd extend this idea of saying what's the total mass. Well, before, right, we had, so remember these are distributions, so your dm are little infinitesimal mass elements in the whole system, the total volume, if you want to call it, or the total mass of the system, whatever. So some block of region. So in that case, right, the total mass is equal to the sum of the individual elements if they were discrete. So this is what we had. But now we're going to convert this into a continuous distribution. So it'll be dm over the volume. We're integrating over the total volume that of these infinitesimals of masses. Next, once we have this, we can now define the RCM, the position vector of the center of mass, to be 1 over m. So in terms of discrete, it was just n particles of mi weighted by mi over the total mass of the position vectors. But now we're going to change this into an integral. So the integral is basically r vector, the position of the differential mass element, integrated over the volume. So this is what I'd like to calculate. So let's try some examples that we already know of. For example, we know that, so before I do this, so a center of mass is effectively where the mass is located. So for example, if I have, let's see if I can find a little stick or something. Okay, here. I have a yardstick. Okay, so if I take this stick, the effective mass, right, of the system is somewhere in the center of this stick. Let's see. You can see the whole stick. Yeah. And roughly, if I balance everything, right, that's roughly about where it should be. Now, actually, what I'm doing the balancing, right, I'm actually calculating the center of weight, which is slightly different from center of mass. But I'm not discussing that today. But so we're discussing the center of mass. So effectively, this point right here, roughly, right, is where the total mass of the system is located. Right at this point, in the center of everything. Right where this bubble in the leveling glass is. Anyway, so so let's calculate this, and we'll assume that we have a coordinate system, and we have a stick. So here's our example. We're going to calculate find center of mass for stick. So I'm going to assume the stick, right, lies in it's got a length of L, from here to here. Let's assume it's the y coordinates and the z coordinates is coming out, and it's lying on the x-axis from 0 all the way to L, and the differential mass element dm, and its distance from here to here is x. So let's calculate. I assume that this mass of the stick has to have a stick, mass m, and length L. So we want to ask, where exactly is the center of mass? I think all of us know exactly that the center of mass of a uniform stick is somewhere in the center, so we'd expect it as 1/2 L. But I'm going to actually do the calculation to make sure we can actually do these calculations. So we're going to go through the position vector of the differential mass. So actually, let's calculate the total mass first. But it's kind of silly, but let's do it anyway. So here's our d mass over the total mass of the system, which is basically the mass. So we already knew that. The total mass of the stick is m. So we didn't have to go through this. But how about the RCM? The position vector of the RCM is, actually before I do that, let's find the position of this mass element along the x-axis. So the position vector is going to be located xi plus 0j plus 0k, or simply xi. And so we can calculate the center of mass by just saying it's RCM, the position vector, which is 1 over the mass over the integral over the volume, but we're actually taking integration from 0 to x, so I'll just write it. We're taking it from 0 to the L, 0 to L, of the position vector xi dm, which is r dm. So we're pulling out the I vector, so it's I over m integral x dx taken from 0 to L. And I made a mistake, so let's fix that right now. This m, since this is x, right? I'm going to use the chain rule to create a function of x's. So we're switching over into mass per unit x, and so this is our chain rule. But the mass per unit length, right, is actually just not a lot of space. I hope, and the marker is dying. So here, let's put the I outside the unit vector. It's just a constant. 0 to L, and we have x. But what is the mass per unit length? Well, it's a uniform stick. That's what I didn't mention it, but it was supposed to be a uniform stick. And if it's a uniform stick, I'm expecting the mass per unit length to be the same as the mass of the total over the total length, dx. And a couple of things we notice: the m's drop away, the L pulls out, so we're left with I L integral of x dx taken from x is equal to 0 to L. And I think I moved the L up top and it should be at the bottom. Good. Okay, so the integral of x is 1/2 x squared, and limits from 0 to L is just I over L times 1/2 L squared. So that comes out to the I vector L over 2. So we've actually said that the position vector of the center of mass of the of a straight stick, right, is nothing more than just 1/2 the length. So that, I think we all knew that ahead of time, but this is just to get you used to calculating center of mass. Let's try calculating center of mass, something more complicated. So let me erase this. So I think we have the general idea, so let's just erase this and let's do some examples. So imagine that I have a flat plate and it's got a length of L and a width of, actually, yeah, sure, let's make it a width W. So example, and I'm going to put this in the coordinate system along the x and y axis. and I'd like to find the center of mass. And I think everybody knows that effectively the center of mass, where the weight of the system, right, or sorry, not the effective mass of the whole system is located, right, should be roughly in the middle, right over here. So we kind of know that, but let's do it in calculation just to make sure we can understand what to do. So this is actually an example of a double integral, and hopefully you understand it, but this is just to brush up your calculus. Anyway, so we're going to define the RCM, and I assume that this rectangle slab of uniform material has a mass m. Let's just make it simple. So it's got a length, oh, I should say the height, maybe height is a better name, but I called it length and width. Okay, so the length is L and W is width. So length could be 2 meters, width is 4 meters, mass might be 10 kilograms, but I'd like to know effectively what the center of mass is. So we're going to do the calculation in terms of an integration, but so the RCM, the center of mass of the system, is 1 over m over the integral of that whole region, let's call it R, dm. So this is your region R. And so we're going to change this into an integration. We know that we need to take, so a mass element of dm is located, I'm sorry, I forgot to put position vector. It's located at x, so if this is the x coordinate, so I can say that the position vector of the mass element is xi plus yj. So xi plus yj times dm. But I'm going to say that this mass per unit area, I'm going to use the chain rule, but I'm also going to say that the area element, right, is actually a dx dy element, which is a little rectangular square, right, that has a width of dx and a height of dy. So this is your dA element. So we used chain rule and then we cascaded it into a two-dimensional integral. So converting this into a two-dimensional integral, I'll put the y is going from 0 to L, y values. X is taken from 0 to W. This is W, and this is L, right, at that endpoint. And we're taking xi integral plus yj. What is the mass per unit area? Well, it's basically the total mass divided by the total area of the system because it's uniform slab. So this is mass times length times width, and dx dy. So we can calculate this center of mass, right? So we can calculate this as, we can pull out the m. Well, actually the m's cancel, so we don't have to worry about that. So now we have 1 over L times width, and we have an integral taken from xi plus yj dx dy. Okay, so I'm going to convert this into a double, the sum of two integrals. So this is now equal to 1 over LW, and I'll put an I here, integral of x, I'm sorry, these are two integrals, right? Have it 0 to L, x is taken from 0 to W, from 0 to L, x is equal to 0 to W of x dx dy plus 1 over LW j integral y is equal to 0 to L, x is equal to 0 to W of y dx dy. Yeah, I think this marker's had it. Okay, so we can integrate from x, this is 1/2 x squared, from 0 to L. So this becomes, the first integral is 1 LW. We have the I, and then we have y is equal to 0 to L. The integral of x to 0 to w is 1/2 x squared, or integrated from 0 to w, so that's 1/2 w squared. And then we have a dy. On the second integral, notice the y, it can come out of the integral because it's not a function of x, so the y can come out, and then we're integrating x, so this is really the integral, 1 over LWJ plus, taken from y is equal to 0 to L of the y pulling out and integrating is just x from w, so this is really wy dy. So we have two integrals to solve. So 1/2 w squared is a constant, we can pull that out, and then you're integrating, so this is just L. So we get 1 over LW times I, and then this is 1/2 w squared because it's coming out. Then we're integrating this with respect to y. 1 dy is just y, so that's just really L. So that's the first portion. The second integral, LW is, oops, the w can come out, so we have a w coming out. Then we're integrating y, which is 1/2 y squared, so that'll be 1/2 L squared. And so we can write this finally, actually, let me write it at the bottom over here. So the w squared, the L drops away over here, the w drops the 2, and you're left with I 1/2 w plus, here's a w, they drop away, the drops this L, so you're left with 1/2 L and J. So what you're saying is that the position vector of the center of mass is halfway between each of the points. So it's 1/2 W, this somewhere over here. So this is the RCM. So we already knew this, and it's basically a practice to make sure that you're understanding these ideas of what these integrals mean. So let me try another example to calculate the center of mass. And something that's so let's do a half a ring. So it's not trivial. So imagine that, find CM of, and I'll be lazy, so I'll actually put half a ring from here to here, and let's assume it's got a radius of R and it's got a total mass of M. So we have a ring, a thin ring. Okay, so, and I'd like to know where the center of mass is located. Notice the center of mass is somewhere in that half circle, somewhere over here. I don't know where, but let's find out. Let's find out what it is. So we're told that it's got a radius of R and it's got a total mass M. Find CM of ring, half ring. A lot of writing. Okay, anyway, so here's our example. And let me erase this, and we're going to do the same calculation over again. So these are mechanical processes, so you just have to get used to these integrals. So what is the total mass? Well, we know its total mass is M, but let's calculate the RCM. So the RCM, the center of mass, is defined as 1 over mass times the integral, the total mass of the system, over this ring. So actually I'm going to take each point, because we're used to like polar coordinates, so I'll just say this is theta. So just to do it in terms of theta. So I'm going to be integrating in R dm is going to be integrated from theta, and I'm going to select this to be minus pi over 2. Down is minus pi over 2 to pi over 2. So our position vector, right, if you kind of remember polar coordinates, we're expecting that the position vector should be r cosine theta I plus r sine theta j. And so, but because I'm kind of lazy about this, so we have to make sure we convert everything in terms of theta. So I'm going to divide by d theta and multiply by d theta. Actually, it might be a little bit easier to do it a different way. So let me not do in terms of d theta directly. I'm going to say, let's take a little segment of it as ds. ds is the arc length of this little angle, so dm. So I'm going to take it in terms of ds times ds. But that integral, right? But we know that if somebody gives you an arc length of a circle like this, of a half circle, this arc length and the radius r and theta are related by s is equal to r theta, as long as we're working in radians convention, then ds is equal to r d theta. So I'm going to be chaining this. We chained originally with s, now we're chaining with theta, so it's d theta. So this is my integral that I'm going to calculate. And what is the mass per unit length? Well, that should be just, I know that the mass per unit length, right, is the total mass over the length of this ring. So we know 2 pi r is the full length, so it must be pi over r. So the length is just pi over r. So we know this length. So we have ds d theta is just r, so this is r, and d theta, and we can start plugging things. So our integral, right, is basically 1 over m times an integral taken from theta is equal to minus pi over 2, to pi over 2 of the position vector, and the position vector is given by r cosine theta I plus r sine of theta j times dm ds, the change in mass per unit length, that was just m over pi r. And then we have r d theta. For ds d theta is just r and d theta. So we can actually notice some things cross out, so we know this r cancels out, this m cancels out this, and we're left with an integral. So we have an I integral first, which is theta, and do you notice the r coming out here? So that's an r that comes out. This is theta taken from minus pi over 2 to pi over 2, and there's a pi coming out of there, so we should remember that. So r over pi over 2, theta is minus pi over 2 times cosine of theta d theta. The next integral is the j component, which is, again, we'll get r over pi. There's an r coming out, there's an r coming out, and there's a pi coming out. And the integral is taken from theta is equal to 0. Can you see this on the board? Yeah, it just barely covers it. Okay, so this is from minus pi over 2. And this is sine of theta. Great. Did I miss anything? It looks correct. Okay, so and these markers, they're dying. Let's see if I can salvage some markers. Okay, so this cosine theta, the integral of cosine theta is, so the derivative of cosine of theta is negative sine theta, but the integral is sine theta, so this is actually just sine theta. So the first integral is just I times r over pi, taking the limit of sine of theta taken from theta is equal to minus pi over 2 to pi over 2, plus j vector r over pi, and the integral of sine of theta is minus cosine of theta, and that's taken from theta is equal to pi over 2 minus 2 pi over 2 positive. And if you think about it, right, this j component, right, cosine of pi over 2 minus pi 2 is 0, so this whole term is 0. These markers are gone. Let's see if there's anything that survives. Oh, that looks a little bit better. So sine of theta is pi is plus 1. Sine of minus pi over 2 is minus 1. So this is 1 minus minus 1, which is 2. So we're getting 2r over pi I is the RCM. This is the position vector of the center of mass. Okay, so hopefully you've understood the general procedure of calculating the center of mass. And I guess in the next video we'll actually spend more time calculating why the center of mass frame is important.